Hola, hi, this is Al, your statistics instructor. Let's get to work. So, in this video, what we're going to try and do is to apply all of the ideas that we have discussed over the entire semester to find a model that is suitable for a time series. Okay, so here we go. Let's refer to our lecture notes. Okay, so you'll find this example in our lecture notes on our Quercus webpage. Also, that file, deaths.dat, is also available on our Quercus webpage. Okay, so that file contains monthly data about accidental death figures in the US from the year 1973 to 1978. Okay, so first step, as you can imagine, we're going to be doing this using R. So let's launch R. So it's already there for me. Now, what you need to do first is create a folder, okay, a local folder. Let's say that you call it sta457, okay. Once you have created that folder, you save the file deaths.dat, and then what you want to do is to change your working directory. Okay, so just change your working directory. This case, mine, it's already there in the folder where I saved the DAT file that we're going to be analyzing. So once you find the right folder, just you set it as your working directory, your new working directory. Okay, so now let's go back to our lecture notes. On the next slide, you will find the necessary R commands to read that file. So you have used that command before, read.table. The syntax is the same that you have used before. You need the name of the file, and then this argument here, header equals false, is in this case letting R know that the first row doesn't have the name of the variable. The first row already contains data. Okay, let me show you what we have here. So let's copy paste the first two lines. Let me just type the name of the object we created, deaths. Okay. So we, in this case, don't have a name for this variable. Okay. So, and all these are numbers. Okay. Let's go back to our lecture notes. So now what we want to do is to create a time series plot. So since we know that the first year where we recorded this is 1973, we set start equals 1973. And since we know that we're dealing with monthly data, we set freq, as in frequency, equal to 12. Okay? Let's copy paste. Okay. Now, let me show you what this looks like. So now it looks so much better. We have years, we have the corresponding months, okay? So actually what we are doing here is we are turning those numbers that we had before, okay, with the command ts, we're turning this into a time series. Okay, now that it is in the right format, now that it is a time series, we can create a time series plot. Okay, so let's do that. ts plot of deaths. Okay, so that's what it looks like. Okay, as you can see, this time series is showing cycles. Okay, it is showing what we call seasonality. So before we can analyze that, somehow we have to remove that seasonality. Okay, makes sense. However, it seems to be fluctuating around constant, right? You could approximate this with a horizontal line, but yeah, the problem is that we seem to have cycles. As I said, we seem to have seasonality present in this time series. Okay, so we're going to, as I said at the beginning of this video, the idea is discussing a general approach to analyze time series. Okay, so we would like to remove those cycles. We would like to model that seasonality. And the general approach to model a time series like this one is to represent that time series as a sum of different components. Seasonal component, trend, and the residual term. Okay, so first let's deal with this guy, with the seasonal component. So remember from what we have been doing lately when we started talking about spectral analyses. So what we said is that we were interested in the spectral density and the normalized spectral density, because then we could find an estimate for the spectral density of a time series using a periodogram. And the periodogram would allow us to discover, to identify the important frequencies, okay? Important frequencies that we could use to model seasonality using sines and cosines, okay? So our first step in dealing with that seasonality, as you can imagine, is making a periodogram for this time series and trying to identify the relevant frequency for this data. Okay, so let's do that. As you remember, to construct a periodogram, the raw periodogram using R, we are going to be using this function, spec.pgram. Then syntax of that function is you need your time series. We have already turned those numbers that we had into time series. Then this argument, fast equals false, is letting this function know that we don't want to use the fast Fourier transform to find it. Okay, this one, remember that this function can find you a smoothed version of the raw periodogram, but we want is the raw periodogram. Okay, now this is an additional argument that maybe you haven't seen before. This log represents this. By default, this function here, spec.pgram, represents the y-axis using a logarithmic scale. So that's the default, but we don't want that. You'll see that in this case, it's nicer to have it in the regular scale. Okay, so that's what we're saying. Let me just copy paste this. And this is our corresponding periodogram. Remember that R is not going to be graphing here on the horizontal all the frequencies. In this case, we're talking about monthly data. So regularly you should have from 1 to 0 to 12, because we're talking about months. And these are the W's, right? So this would be 1 over 12, 2 over 12, and so on, right? Okay, so the thing is that from what we did before from a previous video, we know that the periodogram is going to be just graphed up to half the entire period, because we're taking advantage of the properties of sines and cosines. So this is enough, having half of the period. Bottom line here, so the most important frequency that we have here is this one. W equals 1, so it would be 1 over 12. So if that's the frequency, right? So if the frequency is 1 over 12, that means that the time period is the reciprocal, right? So 1 over 12, the reciprocal would be 12. Now, if you think about it, that makes sense. Let me go back to the time series plot. And then you go, oh, so here you have 1973. Chances are this is the first month of the year, right? And then you have 1974, and again, you have that kind of a minimum. 1975, first month of the year, another minimum, and so on. So it makes sense, right, that the important frequency is 1 over 12, and remember that time and frequency are they are reciprocals of each other, right? So again, so if you have that the frequency, the important frequency is 1 over 12, the period is going to be 1 over frequency, so 1 over 12, that gives you 12. So what that is telling you is that you have a repetition of the pattern every 12 observations. Makes sense? So every year. Okay, so we have something like this. We did something like this here. Next, so we, thanks to the periodogram, we have identified that we have this seasonality every year, okay, this yearly cycle, okay. So now let's try and model that, okay. So we're going to be using sines and cosines that are going to help us model that seasonal pattern, okay? On the next slide, I'm going to show you how we're going to be doing that. What we're going to be doing is we're going to be using a linear model that contains cosines, a cosine term and a sine term using that frequency that we have identified as the most important one, thanks to the parallelogram. Here we go. So first, note that the mean for our time series, let me go back here to the time series plot. Note that if you were to use a horizontal line as the average here for that time series, that is not 0, right? So let me do that. Let me find the mean for that time series and remove that mean. Okay, so that's what we're doing here. We're correcting the time series by the mean. Okay, then, so now we have a time series with a mean of 0. Next line of code. N, the sample size, is obtained with this command, length of your time series. Then, as I said, what we want to do is we're going to be modeling that seasonal pattern using a linear model. So let me construct the design matrix for that linear model of yours. So I'm going to be using time as one of our predictors. So it's going to be, you know, just a variable, a sequence of numbers that goes from 1 up to the number of observations that we have. So 1, 2, 3, up to whatever this n is, okay, the number of observations in our time series. Then I'm going to be creating a column of ones for that design matrix, okay. Then the next column in our design matrix will be a column with the cosine of that important frequency, okay, that we found here, 1/12. That was the frequency, right? And then we're going to have that multiplied by t, by the time. We're going to do something similar for the sine. Okay, again, we're using that important frequency, 1/12, that we found using the parallelogram. Then we paste, we combine these 3 columns, that vector of ones, that vector with the cosine of 2 pi times the time at that important frequency that we found using that parallelogram. We do something similar with the sine. So we have the sign matrix X. Remember, that's what we used to call it in linear regression. So that X is going to be a matrix with n rows and 3 columns. Make sense? Okay. Now, at the end, what we do is we use that LM function. Remember that that stands for linear model. The syntax of that function: first you want your response variable, the variable that you're trying to predict. Then here I'm placing that design matrix that we created. And then this -1 is underlying that, hey, my design matrix already contains the y-intercept, that vector of ones. Okay? So let's do that next. Okay, and just let me show you what the design matrix looks like. Let me type X. See, it's a matrix with 3 columns. Okay, the first column is a column of ones. The second column is the column of cosine. The third column is the column for the sine term. And then it seems that we have 72 observations. Okay? Okay. So we use that design matrix to fit a linear model. Now remember this summary command allows you to carry out a hypothesis test, t-test for the individual coefficients, okay? And it also provides the values of those coefficients. So in this case, we're going to have a beta 0 hat, which is the estimate for the y-intercept. You're going to have a beta 1 hat for the cosine. You're going to have a beta 2 hat for the sine term. Let me just copy paste this. Make sense? Okay. So this is, well, these guys are the estimates for beta 0, beta 1, beta 2, okay? Standard errors, t-values, so on. So as you can see, both coefficients are significant, meaning that they are different from 0, okay? They are useful predictors. So let's keep going. So that's exactly what you are seeing on the R console. You have that also in our lecture notes. Next. So what we're going to be doing next is we're going to be using that linear model of yours, and we're going to compare your time series, your observations, values from your time series, and the predictions you end up with just using this linear model. Remember that this linear model is going to be modeling the seasonality that we observed, okay? Okay, so remember that one way of getting the y-hats, your predictions from your linear model, is just, let me just show you this. So this is the name of the object that we fitted in R, that linear model, right? So remember that if you type names and then the name of the object that contains your linear model, you have the objects contained there, the elements contained there. So you have residuals, you have fitted values, and so on. So in this case, these guys are our predictions. So that's what I want you to see, that those guys are, in this case, the seasonal component, okay? Here we go. So if we want to isolate one of those objects contained in fit underscore deaths, what we do is this, just name of the object, $, and then you could be lazy. Instead of typing fitted values completely, you can get away with just typing the first few letters. And then I'm turning those predictions into a time series object. We want that to start at 1973, and we know that we have monthly data, so what you want to do is set freq equal to 12, okay? And then I'm calling that the predictions from your time series, so preds underscore ts. Then what I'm going to be doing is plotting the original time series, and then I'm going to add the predictions using our linear model. You'll see it in a sec. Let me just clear my console here because it looks kind of cluttered. Okay. Let me show you that graph. So that's the original time series plot, okay? That's the original data. Let me go back here. With this, with lines, we're going to be adding those predictions that come from that linear model that has as predictor variables that cosine and that sine with the important frequency that we identified using the periodogram. Remember that we corrected the series, we mean corrected the series, meaning that we subtracted the mean. Okay, so now we're doing the opposite. Okay, we're adding the mean so they are at the same level, our predictions and the time series plot. Okay, with that LTY argument, I'm just telling R that I want a dashed line, I want a blue dashed line. With this command, legend, I'm going to be adding a legend to make it more readable. Top right is going to control where that legend is positioned. And then, since first we made first on our scatter plot, we presented the observations. That's the first label that I want. And then we drew the predictions. Then I'm using that label for the predictions. Next. This LTY is the type of line that we're using. This was a regular one, a solid one, so that's a 1. In this case, it's a dashed line, so the type of line that we're using is 2. Colors, the first one was black, second one for predictions blue, and then this BTY is by default, legend is surrounded by a box. I'm using that command to remove that box for the legend. I don't want it. Okay, so here we go. Let me see, guys. And yeah, let me just, over the existing time series plot, I want the predictions and that legend. So let me show you the new version. Okay, so again, that blue dashed line is that seasonal component that we found using the periodogram. So now, what we can do is from the original time series, we're going to remove that seasonal component. Okay? That's what we're going to be doing next. So, just like we have our fitted values, you guys know that a linear regression object contains also residuals. So what we're going to be doing now is we're going to be modeling those residuals. We have already modeled that cyclic component, the seasonality in our time series. Now what we're going to be doing is modeling the residuals, that random fluctuation component. Okay? So with this, we're going to obtain the residuals. We're going to save the residuals in an object called this _ the season. And then let me make a time series plot for those residuals. Okay? Paste this. So that's what we should end up with. Let me go back to R here to see if we were able to produce the same graph. That's the case. Okay. Now what I want you to see here is that our residuals contain kind of a quadratic term. So it seems that there's, after we removed that seasonal component, we still have a trend present. Okay, so let's try and remove that trend component. Okay, so that's what we're going to be doing next. As you can imagine, again, what we're going to be doing is using regression to remove that trend component. Okay, so what we have on the next slide is just a reminder of this observation. Okay, that we have a seasonal, that we have a trend present in our residuals after we removed the seasonal component. Okay, so let me show you the Rcode that we're going to use to model that trend component. So again, let me use n for the length in this case of the time series that doesn't have the seasonality anymore. Again, let me create a predictor called time. It's going to be a vector that goes from 1 up to n, the length of the deaths, without the seasonality component. Okay, just like before, I'm going to be creating a column of ones with the command rep 1n, so we're going to be repeating the number 1 n times. That's going to be the first column of our design matrix. Now, since we had previously created time, now what I want with this time too is the quadratic term. So all that I do is I square time. And then with that command cbind, as in column bind, I'm pasting these three vectors as columns so that uppercase T is going to be my design matrix, where the first column contains just a bunch of ones. This one contains the time as a predictor, and this one contains time square as a predictor. Okay, so we're doing something similar to what we did with the sine and cosine terms to capture the seasonality in our time series, but now we're modeling the trend, okay, and using time and time squared as a predictor, as predictors. Okay, so let's do that. Let me copy paste. Just like before, let me use the summary command to find the estimates for the linear model that is going to help us capture that trend component in our time series. And not only the estimates, we're going to find out if they are statistically significant, meaning if they are actually there, if they are different from 0. Okay, so here we go. So again, they are different from 0, these coefficients. Okay, the one for time, the one for time squared. And now this is going to help us model the trend that we are seeing in the residuals after we have removed seasonality. Okay, so now what we're going to do is, after we have removed that seasonality, right, now we're going to use the residuals after we have removed seasonality and trend. Okay, so this guy here, that RES object, contains the residuals after we have, as I said, removed seasonality and trend. Let me show you a time series plot for those residuals. So much better, right? Now, these residuals seem to be fluctuating around a constant. They seem to be fluctuating around 0. So much better. Okay, now next, let's find out if if we could model these residuals using some of our fancy time series models, like an ARMA or an ARIMA model. Okay. So first step, how about we make the a graph of the autocorrelation function. Okay. Okay. So let's do that. So as you can see from the autocorrelation function, this doesn't seem to be the autocorrelation function corresponding to white noise, right? Because we have these, we have several of these, right, going beyond these two blue horizontal lines, which we know are just a graphical way of carrying out those sequential hypotheses tests, right? If we had white noise after maybe lag 0, right? So we would see that all of these guys would be within the blue dashed lines, and that is not the case, right? Well, except for random fluctuation, right? But these are clearly outside those, right? Beyond those blue dashed lines. So this doesn't seem to be white noise, but let's see if we can capture that behavior that we're seeing in residuals after we have removed seasonality and trend using our time series models. Okay. Okay. So next, let's use that library that we have used before, the library forecast. So if you have already installed that before, don't worry, you don't have to install it again. But every time that you're going to be using this package, this library, you have to load it. So that's what we're going to be doing with the command library, and then with auto.arima, what we're going to be doing is we're going to be fitting an arima model for those residuals after we have removed seasonality and trend. Okay. So as you can see, using that auto.arima function, now what we have is that the residuals after removing seasonality and trend, could be modeled using an ARMA 1, 1. Okay, and this is the coefficient for the AR part, for the autoregressive part, and this is the coefficient for the moving average part. Okay. Now, let's try to summarize the whole analysis that we have carried out. So, as we said from the get-go, the idea is decomposing our time series as a sum of 3 components. A trend component, right? A seasonal component, and then that random noise component. Okay, so for the trend component, in this case, remember we had that quadratic function. For the seasonal component, we have that sine and cosine terms. Okay, and for the random noise component, in this case, we ended up with an ARMA 1, 1 model. Okay, so finally, let's summarize, let's show what our model looks like. An expression for the time series model, or the model that reflects the behavior of our time series. Okay, it looks like this. So you have that y-intercept here. You have the cosine term. You have the sine term. Again, these are used to model the seasonality present in your data. Then, from the trend analysis, if you will, you have another y-intercept. You could combine these later if you want, but I'm just doing this to be very clear about what we're doing. So remember that we had that second linear model that is helping you model the trend. Okay. And finally, this is the ARMA part of your model. Make sense? But again, the idea is you have a trend component, seasonal component, random fluctuation component. Okay? Well, thank you so much, guys. See you on the next one. Take care. Bye.